Okay, so welcome back. From the last video, I told you try B, C, and D on your own. And I know that the majority of you probably didn't do it, so don't lie and fidge your way out of it. I know. I could have eyes everywhere. I could be staring at you right now through your video camera of your computer and you don't even realize it. Okay, so let's take a look at B, C, and D. And if you followed the template for A, you should be okay for B, C, and D. And everything is really the same theme. We're starting with an alcohol, and that alcohol is called butanol. And we're taking butanol, and we need to make B, which looks pretty nasty and ugly, C, which also looks nasty and ugly, and D, which looks even nastier and uglier maybe, with the C triple bond end. So how do we do it? How do we make these compounds from just something as simple as one butanol from what we've talked about so far in the lecture? Let me show you how easy this is, folks. All right, so this is kind of where we left off. Let me clear this out, and let me start with B. All right, so B tells me, starting with one butanol. Okay, but is 4, so 1, 2, 3, and 4 with an OH group. And I have to add something to that. And I have to end up with something that looks like this down below. CH3, CH2, CH2, CH2 with an O on a carbon that has a double bond O with a CH2 and a CH3. All right, so here's the deal. How on earth can we go from the top to the bottom using only what we have learned in Chemistry 251, ding, 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 and our new alcohol reaction? And there's only one. There's just one alcohol reaction. Oh gosh, what is this lecture going to do to me? Okay, so let's take a look at the top. 1, 2, 3, 4. I'm starting with 4 carbons, aren't I? Look at this. If I look at my product, 4 carbons in a row, look, 1, 2, 3, 4. So this is probably my butanol piece, right? These are the 4 carbons that have came from the butanol that the question told me that I had to start with. So that piece is already there. It's taken care of. I don't have to do anything with that as far as the product goes. What I do have to do, though, is I'm going to have to get rid of this OH group that's here at the end, and I'm going to have to replace it with this group because that is what is different. Again, it's like a Sunday cartoon. In the back of the classifieds, you'll find the cartoons, and sometimes you'll see those little games, and it says, what is the difference? Spot the difference. We just did. We spotted the difference here. So I need to get the OH off, and I need to replace it with what's down there at the bottom. So how do we do it? We need to make OH ugly. All right, so how do we get it to be ugly? We give it a black eye, right? We need to give it a black eye through the addition of something like HBr. And if I can get HBr into the solution with that alcohol, the HBr will give the OH, pow, a black eye, and that carbon's going to look at this OH and go, ew, I don't want anything to do with you anymore. You're not pretty. And that OH group goes off. It becomes a very good leaving group. And what goes on in its place? A bromine, folks. A bromine is what goes on there. All right, so if I can add HBr in the very beginning, we have CH3, CH2, 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 and now we have a Br that is on that molecule. So the OH group has left. It has left in form of a water molecule. I don't really have to write that if I don't want to, because this is the major product that we're after, right? So I need to go one more step now, because that does not look like down here, right? I need to add this group on. So how do I do it? What do I add on to get that bromine off? Well, keep in mind, bromine is very ugly naturally. It doesn't need to be given a black eye. It's just that ugly. And that carbon's going to look at this bromine and say, you're going to be okay for now. But if something else pretty comes along, you're out of here. Just forewarning you, you're out. And bromine goes, okay, I'll enjoy it while it lasts. So this molecule stays around for a little bit until I add on a better nucleophile. Something has to come that's a little bit prettier in the club, right? So here comes this nucleophile. What kind of nucleophile? What do you want to add? Yeah, it's that simple, folks. What do you want to add down here? You want to add the O and the carbon and the double bond O with the CH2 and the CH3 group, right? So that's the nucleophile that you add on. That's perfectly okay. That oxygen's going to carry a negative charge. By definition, it is a nucleophile. It's negative. And that piece walks into the bar, and that carbon looks at that O-containing group and says, oh, well, you know, you're a little bit prettier than the bromine that I've got beside of me right now. Move over, bromine. A new person's just walked through the door. And now we have a substitution reaction that takes place. So bromine leaves, and in its place comes the OC double bond O CH2 CH3. And folks, that is how we end up with that product that we want in the very end. It's a two-stepper. It's a two-step synthesis problem. You gotta make the OH leave. After the OH leaves, you then bring in a nucleophile that's a little bit prettier than that one, and corresponding to bromine, and then those will switch, and you end up with the product that we're after. All right, so that was no different than part A that we did before in the previous video. Now, let's look at part C. We have CH3, CH2, 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 and OH yet again. It tells me I have to start with one butanol every single time. So we've got to figure out what do we add in order to get this product that's down at the bottom. So it's going to be a CH3, a CH2, a CH2, a CH2, and then an NH, and then a CH2, and then a CH3. All right, do the process that we just did for part A and for part B. Look, 1, 2, 3, 4 carbons in butanol. All right, 1, 2, 3, 4. There's 4 carbons in that structure. So I don't really have to do anything there. I need to make OH ugly, give it a black eye. Pow! Right? So that OH will leave, and then we can replace that with a group that we want. And the group that we want here is that NHCH2CH3 group. All right, so follow the template that we have just put in place for part A and part B. So in the first step, folks, you need to add an acid. This is the way that we get, pow, an OH, a black eye. That's the way that we do it. So we protonate the OH group, and what we end up with now is a CH3, CH2, CH2, CH2 with a Br on in place of the OH. Now that we have that bromine on, it's a very ugly group. It's a very good leaving group. It doesn't take much effort for carbon to kick the bromine off as long as something else prettier comes into the bar. And that prettiness is going to come from the group that we're after here. NHCH2, CH3 with a minus. So there is the nucleophile, and that nucleophile will come in. It will substitute that bromine out, and now we have a new bond between the carbon and the NHCH2CH3 group. Folks, that's all that you have to do with these types of problems. Dirty up the OH, make it go away, make it ugly. You halogenate that compound, and then when you get to that point, the halogens are the ugliest of all the nucleophiles pretty much. So you can add whatever you want to add on to get that bromine out of there, okay, in the terms of a substitution reaction. That is how this works. All right, so we've got one more, and that's going to be D. So let's take a look at it. Is it going to be any different? So CH2, CH or CH3, CH2, CH2, CH2 with an OH group. All right, so there we go. And we need to add something to it. What do we add to it? Well, we got to figure out what we need. What do we need to make? And in this case, it is a CH3, CH2, CH2, CH2 with a carbon and a triple bond N. Just like before, we start off with 4 carbons. This group has 4 carbons in a row, so it looks like I need to add on this C triple bond N. That's really the major difference here. But OH is very pretty. We need to give it a black eye. Pow! How do we do that? We add an acid. I just like to use HBr because bromine is one of the uglier ones out of the halogen group. I mean, I could add HCl, I could add HI. There's complications with each one of those. HBr is just somewhat of a Goldilocks halogen, and that's why we use it most of the time. So when we do this, that H is protonated on, or the OH group is protonated by the HBr. That forms a very good leaving group, and we end up with a CH3, CH2, CH2, CH2 with a Br. And at this point, I need to get the Br off. That's very easy, though, at this step. I just add on a better nucleophile. And what I need to add on is what I need in the product, and that is a C triple bond N with a minus. Folks, if you can do this, you are one step ahead now in the alcohol reactions. That's right. You just got to kind of look at the template. You just got to figure out what to do as far as this step goes. How do we get the OH off? That's always the very first question. We protonate, protonate, protonate. It's like when you find a house, location, location, location. The same thing happens here. A couple of things I want to say, though. We take advantage of things. Right? We take granted the fact that I can just bring in a C triple bond N minus, or that O, C, double bond O, CH2, CH3 minus. Well, those have to come from somewhere. We do not get these from just a simple old jar that's in a laboratory somewhere. I cannot order a bottle of C triple bond N with a minus on it. Okay, that doesn't exist. So these typically come from a sodium or potassium almost every single time salt. So I can order salts of these nucleophiles, and the salts do what salts do. They typically break down in solution, and they separate out into the ions. So Na plus goes out there, K plus goes out there, depending on which one you use. And then C triple bond N minus just continues to float around. It's freed up. This is a way that we get these negative pieces very easily into a reaction. So I don't want you to take that for granted, and I also don't want that to kind of throw you for a loop if they decide to say, hey, we're going to add NaC triple bond N, blah, 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 blah. It really means the same thing. It's just the source of the negative piece for you. That's all that it is. Again, we cannot order a bottle of negative pieces. That doesn't work. They have to come from somewhere, and very often, even in a textbook, they leave these off. Now, is that the only way that we can get them? The answer is no. We can get these negative pieces from organic molecules as well, but this is typically one of the easiest, and it's typically one of the cheapest ways in order to get it. So there's options out there, but sodium and potassium salts are typically very, very common in the world of organic chemistry. The other thing I want to do is talk a little bit about the organic mechanisms. Okay, so I'm going to go back to the very first one. So CH3, CH2, 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 and then OH. And then we said we added HBr to that. That was the very first step. So I'm talking about part B that we did first in this video. I want to go through and I want to talk about mechanism. It seems like a lot of people just suffer with mechanisms. They don't really know how to draw curvy arrows. They don't know how to predict things. They don't know how to show it on a sheet of paper. And anytime I can review this, it's very good for you, I think. So that's what I'm going to do for part B. We're going to take another step back. We're going to slow it down. And then we're going to take a look at the actual organic mechanisms that take place. Not just add this, we get this. We need to kind of show it sometimes, and that's what we're getting ready to do. All right, so general recap, general review, because none of this is new material. It's just another way for me to introduce it as a review and a second glance for you, okay? So the OH group has some pairs of electrons on it. They're not drawn normally, but they're understood to be there, so there they are. And the H and the Br is a polar compound, so this Br is a delta negative and this hydrogen is a delta positive. So bromine does have electrons around it as well. There's 3 sets, 2, 4, 6, and 2 from the bond is 8. And that oxygen here, 2, 4, 6 from the line on the left, and then 8 from the line on the right. So 2, 4, 6, 8 in total. So those dots have to be present. but they're typically left off in the drawings because we understand that they're there, and we assume that you understand that they're there. All right, so the first step in the reaction here, mechanism. I start my curvy arrow at the negative source every single time, and I draw it to the positive source that it's going to react with. All right, so there's the first step, the first arrow in the mechanism, and that OH is going to go, ooh, hydrogen, come on. And, you know, hey, I'm in this relationship with carbon, and I'm also in this relationship with hydrogen, but I want to be in a relationship with you too. And hydrogen goes, okay, yeah, all right. So they see a bond or an attraction between each other. But this hydrogen is currently in a relationship too, and that hydrogen, it doesn't really feel wanted. That bromine is electronegative. Again, electronegativity chart. That bromine is going to suck all of the electrons away from the hydrogen, and that bromine is going to take those electrons and say, bye-bye, hydrogen, I don't want you anymore. I didn't need you in the first place. Ah. All right, so here's the first step of the mechanism that happens between the alcohol and the HBr acid. All right, so if I want to do these intermediates and transitional states and stuff, I can. So now what we'll do is we'll do CH3, CH2, CH2, CH2. This had an OH group, but that O got greedy, and now it has the hydrogen from the HBr, right? So this still has a free pair of electrons, but its formal charge is a positive now. Again, go back and review formal charges if that's what you need. And then we have freed up a Br minus at this point. All right, in this step, this CH2 and this oxygen bond, that gets a little weaker. This OH now is going to become a very good leaving group. It's water, H2O. So the oxygen's going to look at the three relationships that it has, and it's going to make the decision, well, maybe 3 was not a good idea. Maybe I shouldn't involve myself with 3 people at the same time, so I'll just make do with 2 instead of 3. Oh gosh, could you imagine if that's how real life was? And maybe it is somewhere at some time at some place. So the carbon and the oxygen bond becomes very, very weak. Oxygen looks at the carbon and says, you know what? I can persuade these 2 hydrogens to do my bidding better than I can with you, because the electronegativity difference between carbon and oxygen is much smaller than that between oxygen and hydrogen. So oxygen has more pull. It has more weight. It can get what it wants with the hydrogens over the carbon. So oxygen looks at this carbon and says, well, it's good while it lasted, but see ya, and away it goes. All right, but before this happens, I want you to keep in mind, this alcohol is a primary. That means that this carbon is attached to only one other carbon. So a substitution reaction is getting ready to happen. The OH group with the extra hydrogen, water, is going to leave, but something else needs to go on in its place, and that's because carbon is a primary carbon. It doesn't want to be by itself. So carbons that are primary undergo SN2 reactions. That's substitution by molecular, which means carbon wants to be a cheater. If carbon's going to get ready to break up with something, it better have one waiting at the back door so it can sneak it on into the house and say, you're my new partner at this time. So that's okay with carbon, because here what we have is the bromine from the HBr. It's out there. It's negative. It's looking for a partner maybe if there's one willing to give it a chance. And this carbon knows that it's getting ready to end it with that OH molecules that was there before. So an SN2 reaction happens. An SN2 reaction means that this bromine, there's my negative source, right, will come in and it will attack this carbon, and it will say, sneak me through the back door. And carbon says, okay, come on. And then this OH group then decides to leave because it knows that it's really not wanted. It doesn't need carbon to tell it. It sees the signs of what's going to go forward. When this goes on, now we have a CH3, a CH2, a CH2, a CH2 with a bromine now, instead of that water molecule. So the water molecule we can represent, we can write plus H2O, and there it is. Now, we weren't really finished with the mechanism at this point, because we then took this molecule, and what did we do? We added a nucleophile, another nucleophile, right? So this was an oxygen that had a carbon double bonded O with a CH2 and a CH3 on it. Okay, well, I can show the mechanism here as well. So a substitution reaction is going to happen yet again. Once more, this is a primary alkyl halide, and those primaries undergo only SN2, which means it has to see two things at one time. It has to cheat. So carbon's in a relationship with bromine. This oxygen-containing group is going to come into the bar. Carbon is going to see that oxygen group and say, hubba, hubba, and then a reaction or an attraction will begin to happen. So I can show that mechanism-wise. I'll take this negative piece, and that's where I'll start my arrow, and I'll take my negative, and I'll point it to that oxygen, or that carbon. And this carbon says, I've got a brand new friend, look at here. And then bromine says, okay, bye-bye, I'm not going to stay back for this. You didn't want me, you found something else, you said that I was ugly, I'm tired of your abuse, and away it goes. And here we have another substitution reaction. That substitution reaction, again, is bimolecular, which means it sees two molecules at one time, basically, two atoms, and it makes up its mind on which one it likes better. And in this case, the oxygen-containing piece down here at the bottom is a better nucleophile, so it bullies that bromine out, and it says, get lost, carbon's mine now. I'll meet you in the street if you're not happy with that. And then all of a sudden, we're downtown Wilmington on a Friday or Saturday night at 2 in the morning with cops and police and a fight out into the middle of the street. You probably have seen it. If not, it's something to witness. All right, so there's the mechanism steps. This mechanism step happened the same way every single time with whatever we did. So for instance, in part C, we did the same thing. 1-butanol, we added HBr. That mechanism step is the same. We protonated the alcohol. That turned it into a very good leaving group. Bromine came in, substituted for the water, and that water was replaced. So there was the first step in part C. It's identical. The only thing that we change in part C is the nucleophile that we used down here at the bottom. So we did not need that nucleophile. For part C, what we needed was a NHCH2CH3, right? And the same mechanism steps took place. The carbon and the bromine was a very weak bond because that bromine's very ugly. NHCH2CH3 came into the organic bar. Carbon looked at it and said, hubba hubba, and then nitrogen goes in and attacks the carbon. A new relationship is formed, and that carbon ends it with bromine at the same time because he's a big old cheater. So that is the SN2 mechanism. So once more, keep in mind, primaries are going to be SN2s. They are the cheats. And then secondaries and tertiaries are going to be the SN1s. The reason that this is very important is because SN1 allows for rearrangement. The SN2s do not. So that is why in part B and part C and part D, wherever the alcohol was, that is where the bromine's going to go, and that's also where the nucleophile will go as well when it replaces the bromine. Nothing shifts. That's very nice about SN2. Now, there's nothing nice about carbon cheating, but it's very nice as far as knowing this is exactly where these groups go onto the molecule. So we need to do some examples with secondaries and tertiaries, right? We need to do some of these examples with secondaries and tertiaries. That way we can get comfortable with the concept of rearrangement. You know, in those cases, carbon's not a cheater. The mechanism pieces stay the same, folks, pretty much. I mean, OH is going to get protonated, the water molecule will end up leaving, halogen goes on, and then halogen gets replaced with a prettier group. I mean, overall, the template is the same. The difference is that secondaries and tertiaries will allow for rearrangement, and that's something that we have to watch out for. So what I want to do is I want you to take a stab at these. All right, kind of test what you learned in Chemistry 251 and then mix that in with what we're doing today. and see if you can predict these reactions, predict the products the proper way. So here's A, B, C, and D. In each case, you're given an alcohol, right? And we see that alcohol group in part A right there. We are reacting it with an acid, and we want to know what would be the product if that acid and that alcohol react together. However, the difference here, take a look. The OH group here is on a carbon that's on two others. So this is a secondary carbon. This OH group is on a carbon, and that carbon is attached to three others. So this is a tertiary carbon. For part C, that OH group is on a carbon that's attached to two others. So this is a secondary. And then for part D, that alcohol group is on a carbon that's attached to two others. So this is also a secondary. Once more, secondaries and tertiaries undergo SN1 reactions. The carbon sees one thing at one time. When the breakup happens, carbon says, I need to get my crap together. I need my life together. I need to improve myself before I bring on a new relationship into the picture. So carbon's going to take a moment to look at its surroundings and say, can I fix anything? And that allows for rearrangement to take place. So in the next video, this is where we're going to pick up A, B, C, D. We're going to predict these products. We're going to talk about rearrangement if it happens, the differences with what these products would be compared to something that you saw before in this video, right? Just straight cut. There's where the OH group is going to go. That's where the bromine's going to end up. And then that's where the new nucleophile is going to go. These, little different. All right, so try them. If you get them wrong, you get them wrong. Nobody will ever know. I'll never know, at least, unless you tell me. And then in the next video, we'll check your answers. We'll work through each one of these problems piece by piece. And that way, when you see me explain them, you might understand where you're messing up and what mistakes that you made in order to give me the answer that you wrote down on your sheet of paper. All right, so that's what we'll do in the next video. I'll see you then. Don't give up on me. Come back. Try these. A few minutes worth at least. Just a few minutes. And then come back. I'll be waiting.